Hello, everyone, and welcome to our webinar. This is part 2 of our series on monodisperse fully porous particles. Jeff Faden, MacMod's president and co-owner, will discuss how this technology can be applied to untargeted metabolomics and lipidomics screens. My name is Edward Faden, and I am the vice president and co-owner of MacMod, and I will be monitoring today. If you have questions during the presentation, please type them into the chat window and include your name and company. We will do our best to answer as many questions as possible in the allotted time. A recording of the webinar will be posted on MacMod's website and LinkedIn page. You will also receive a link to view the recording via email. Before we begin, I would like to tell you a bit about MacMod Analytical. MacMod was started in 1986 and is known for providing innovative chromatography solutions for complex separation needs. We recognize the value of having unique, high quality, and useful analytical tools for scientists and are committed to being a value-added consultative resource for the life sciences industry. Today's speaker, Jeff Faden, is the president and co-owner at MacMod. He received his Bachelor's of Science in Chemistry from Penn State University in 2003 and his MBA from Temple University in 2014. He joined MacMod in 2009 and has served as a trusted resource to the life sciences industry for over 15 years. Thank you for joining us today, Jeff. I'll pass it on to you now to begin.
Thanks, Ed. So I wanted to thank everyone for joining the webinar. Just to show you the executive summary of what we'll be talking about. We're going to reintroduce the monodisperse HPLC column particle technology. We will also go into how it's being applied to an untargeted metabolomic study with our collaboration with the University of Florida, as well as a lipidomics comparison study to an industry standard column, as well with our collaboration with the University of Florida Metabolomics Center. So the product line we're talking about today is called Evosphere Monodisperse UHPLC Particle Technology. It was introduced in late 2022 to basically bring something new to the marketplace. If you get a chance, a recording of the part 1 of this talk, Chromatography in 20 Minutes, is loaded up on LinkedIn and downloadable from our website. So what you see here is a scanning electron microscope image of the particle technologies. And on the left, you see there's some little spheres and big spheres. And on the right, what you see is mainly visually a monodisperse particle, or the fact that the distribution of particles is all the same size. So you might ask, well, how do you measure that? Well, you use a Coulter counter. And the Coulter counter counts the number of particles as a distribution. And so on the left, you have a commercially available 3 micron material. And on the right, you have a commercially available 3 micron material. And then in the center, you have the Evosphere 3 micron material. And how you measure monodispersity or dispersity in general in particle size is you look at the count of particles at the 90th percentile of the Coulter counter comparison and of the 10th percentile. And the closer you divide those two, D90 over D10, closer to 1, that's the more monodisperse the particle is. So what you can see here is how we're measuring that and comparing it to the previous commercial silicas. And we are showing a D90 over 10 of 1.12 as compared to the industry standard 1.6. So that's a 40% reduction in D90 over 10. And that is really one of the significant innovations here that is driving the value of the product line. So what you see here, you've seen this from a number of other vendors. This is the resolution equation. This is a nice graphical representation done by Pete Gar's group at the University of Minnesota. And what you have is an efficiency term, a retention term, and a selectivity term. The way you measure efficiency is you take the length of the column and you divide it by the height equivalent to a theoretical plate. And that is how much, how tight and tall the peaks are. I go into more deeper discussion on calculation of plates in the version 1 of the webinar. So I suggest you look at that to get a view of the expanded Van Deemter as well, and how to calculate it, and how the A term is really what's going to be driving the efficiency here. So what we show is, this is sort of what it looks like with a pictorial version, and the A term in the Van Deemter equation is referencing your multipath effect. And what that means is, as the analytes travel down the column, the less tortuous path, and tortuous meaning, basically multipath, that they can go through the packed bed, the tighter your peaks are going to be. And what you can see here is, this is the same analyte, but 3 of them essentially, going through the column. And on the top column, you can see that it doesn't take a tortuous path, whereas, and this is exaggerated, but the non-monodisperse or polydisperse material has to travel around the particle to get to the side of the column. And so the quickest point between 2 points is a straight line, or the quickest path for that matter. And so what does that mean? That's well and good. What that means is, you get higher plates, 60% higher plates comparatively to the commercial D90/10 silica, that's 1.6. And so that's really advantageous because now you have a more efficient particle per unit back pressure. And so you might say, oh, well, that sounds like an innovation from 20 years ago. That sounds like superficially porous technology. Well, the second innovation here is really how we're maintaining the surface area of the material. The superficially porous technology, on average, in a 2.7 or 3 micron material, is about 130 meters squared per gram. The Evosphere material is 350 meters squared per gram. So what that means is, you can load more onto the column and not have distorted peak shapes. And so that's a significant advantage as well if you're needing to go to isolation purification groups, and or if you're needing to see a small component in a very large drug substance or drug product mixture, the advantage to load more onto the column really becomes advantageous. And so what I would say is, go back again, listen to my version 1. I go into a deeper discussion as to why that is. But I wanted to sort of talk about how we're applying this technology now to different omics work. So this is again the resolution equation, and what we're going to hone in on is the selectivity term. And the selectivity term, if you go back, it's almost linear to resolution. And so that gives you a lot of advantages. The column we chose for the metabolomics work is because you have a lot of small molecules there that are similar. So we chose the C18PFP because it has regioisomer selectivity. For the lipidomics work, we have a novel selectivity called C12. The C12 creates a very hydrophobic environment. And so we're going to show how that is applied there. The monodisperse particle technology applied to metabolomics. This work was done by Dr. Timothy Garrett at the University of Florida. He's had a really good success with the C18PFP. This is what that column looks like. The column was chosen was a 2.1 by 100, 3 micron. And again, the reason why this was chosen was because the C18PFP has regioisomer selectivity, and that has to do with the pentafluorophenyl group bonded to the Evosphere particle. So this is the total ion chromatogram and the arrows there are pointing at which part of the chromatogram we're going to show. It was done on a thermo Q exactive, which is a very powerful MS. It's a plasma extract. It's an untargeted approach. I think the key point here is only formic acid is used, so there's no buffer used in this separation. So very easy to implement onto your new metabolomic screens. And then we give the gradient onto the right. If you want to mimic this work, recognize that your extra column volume and extra column dispersion can come into play. And so there's some tricks there that we can help you with to adapt this method. The first thing here is showing for the monodisperse material, that surface area is coming in and driving, and also the selectivity, the bonded phase, is driving the retention of pretty polar compounds. So 5-aminopentanoic acid has a log P around negative 2.5. So normally in reverse phase, I mean, that's going to show up in your T naught. This is the 100% aqueous portion of the gradient. So you're getting really good retention there, reproducible retention. And also you're getting separation from valine, again, another small polar compound. You're getting nice peak shapes out of it. So really exciting here. Lots of positive feedback. Again, valine's log P's around negative 2.2. You know, and so a lot of times when you see negative log P's, a lot of people would approach this with either a Hillick method or some type of other approach, or derivatization or ion pairing or high pH work. And this is being done at low pH with formic acid, mainly driven because of the monodispersity, the high surface area, and the novel bonded phase chemistry. The crowd pleaser, as Ed likes to say, is isoleucine and leucine. We're able to separate them, baseline separation, and that's just the methyl position switch, and that's coming from the C18PFP. If you look on the isoleucine peak in the front, you're starting to see allo-isoleucine and nor-isoleucine pop out, and so we have some other data later, but we'll show you when we drop the particle size to 1.7. Acyl carnitine on a C18, you would get pretty poor peak shape with just formic acid, and honestly, we're not exactly sure why the peak shape's really good, but to be honest, but you're getting really nice peak shape, which is a nice benefit. You get strong isomeric selectivity here from tyrosine and phenylalanine. You can see that between the two compounds, you only have a hydroxy group on that phenyl. So really exciting isomeric selectivity changes. This one we also show in the lipidomic study using the C12, but lysophospholipid isomers SM1 and SN2. You can see that the waxy portion is in the screen and then going either back into the screen or basically in line with the screen is really the main differences between these two, and you're seeing you know, a nice separation here using the C18PFP if this was to show up in your untargeted metabolomics mixture. So really exciting. And again, I wanted to say that efficiency obviously was, like I said before, the end term dropping your particle size does increase the efficiency. Of course, it also increases the back pressure, so you have to be aware of that. But in this case, 3 micron down to 1.7 micron, keeping the column size the same, and you're able to start pulling out that allo-isoleucine and nor-isoleucine. And I would say, you know, you could even go out to, if your LC can handle it, you go out to 2.1 by 150, and you might start to see that even pop out even further, or adjust the gradient or things like that. So Tim was really excited about this, really exciting work. We've been standing up, has been implemented at a number of clinical labs across the country, and just really wanted to give this type of value to our customers to make sure that, you know, they can solve their difficult separations. He also is doing a lot of lipidomics work, which is really a subset of metabolomics. I think the thing with lipidomics is, you know, when you're blasting these lipids in a mass spec, they break apart, and so you can use the MS to really differentiate. Whereas on the metabolomic side, the column really has to come into play a lot, because it's really retention time that is the marker that you're using to know that these things are what we're claiming they are at the levels that we're claiming they are. To show here for the Evosphere C12 was chosen. This just to show that it has some hydrophobicity, but it also has a little bit of steric selectivity, not so much polarity, and obviously no dipole charge. So the industry standard column is a sub 2 micron, 2.1 by 50, and we used a 3 micron, which is a very high efficiency monodisperse particle using the C12. Now the C12 has an optimal bonding density, so we believe that it creates a very hydrophobic environment. In some cases, depending on which C18 you get from which vendor, can be more hydrophobic or less hydrophobic. But we're not having to use as much end capping. That has secondary benefits. We also have some data to show that the C12 is high pH capable, which is really exciting, because that opens up a whole nother world of applications you can use it for, especially for oligonucleotides and such. So we're really excited about this phase. What I would say the goals of this experiment were to take a method that was established, that had been running for a long time, to not adapt the method, but really just to take a column using a new particle technology, using a new bonded phase technology, and to put it into that separation and see how it does. And I mean, we were really blown away by the results. You have to use a lot of IPA in these methods. This is standard. This is what people do all day, every day. So you can see in the mobile phase B, you have a 90% IPA, 8% acetonitrile, 2% water with 0.1% formic acid, and 10 millimolar ammonium acetate, or sorry, ammonium formate. And then mobile phase A, you have 60-40 acetonitrile water with 0.1% formic acid and 10 millimolar ammonium formate. The flow rate is 500 microliters per minute, which is a good flow rate for a 2.1. A little above the optimum, but depending on your separation. And then the temperature is 50 degrees C. It is a multi-step gradient. So you can see the gradient profile here, and we'll, just so everyone knows, we'll send the slides afterwards. Right off the bat, you can see half the back pressure. That's a significant benefit. Then you can see, the TG envelope to make sure that the mass spec is working properly. This is, standard thing they do. What I'd like to focus on here is the total ion trace. So you have 5 sets of lipids that we're showing. You have lysophosphatidylcholines, you have phospholipids and phosphatidylcholines, and you have the cholesterol esters and the triglycerides. And really just, you can look at the intensity, you can look at the number of peaks, you can look at a lot of stuff here. But all in all, it was surprisingly better. And that was really what we're going to be showing here. So the lysophosphatidylcholine, 16-0, 0 meaning no double bonds, sharper peak, less tailing than the industry standard. The lysophosphatidylcholine, 18 carbons, 0 double bonds, less tailing. The cholesterol esters, I mean, again, sharper peaks, less tailing. You're seeing a theme here coming on, more retention as well for those 18 carbons, 3 double bonds, 18 carbons, 4 double bonds, 18 carbons, 2 double bonds, 18 carbons, 1 double bond. You have the phospholipids. You have the competitor C18 on the left. I mean, the first one, 38.6, this was significant at half the back pressure. I mean, just so we're all clear, half the back pressure and a little bit more retention too. So you get to play around with the gradient and things like that. If you wanted to optimize this further, 36.4, you can see it's just higher, taller peaks. And that's really the name of the game when you're trying to identify what lipids are in your study. The PCs with different degrees of unsaturation, again, it is really exciting. You can see just really tight peaks, pulling out other peaks that are there, especially the 34.3. Didn't look so hot on the industry standard one, so you have a lot of coelution there. We're starting to get a little bit taller, sharper peaks there. And then we look at the triglycerides. This is 44 to 48 total carbons, tighter peaks, tighter, taller peaks. We believe it's the monodispersity, the surface area, and the bonded phase hydrophobicity. So that three-pronged approach of innovation is really what we're driving here. And then we have the triglycerides with 52 total carbons. Again, tighter peaks. You're getting a theme here, but that's essentially what we're talking about. And then we wanted to hone in on this one because you can really see just how much efficiency gain you're getting at half the back pressure. And then the half the back pressure piece was really exciting because he's like, okay, well, I can really push the flow rate then if it's at half the back pressure. And if I wanted to move this possibly to, and we had a request from that partner, hey, can you do it in a 5-minute method? And we're like, whoa, that's pushing the envelope. And this is a 22-minute method, soup to nuts. And we did complete that work, and we have an application and an email that'll be going out on a 5-minute method. What I'd like to say is we also have an email with this. This will have an application note that you can share around to your colleagues. And just lots of, we have some other data that is coming out. So lots of data coming out on this new monodisperse particle technology. We've been talking about it a lot. Happy to discuss your specific issues, your specific, trouble set, putting the right column into the right situation. And with all that being said, I'd like to thank you for attending. Again, you can go back and review. I go into more deeper studies on the particle itself in webinar part 1. This was part 2 showing the metabolomics and lipidomics work. And then we're going to be doing a part 3, which we're really excited about, on how we're applying it to oligonucleotides. So with that being said, thank you very much for your time, and get back to your day doing those separations.
Well, thank you, Jeff, for that wonderful presentation. We have a few minutes to answer some questions from the audience.
Cool.
You can type any questions into the chat window. Please include your name and company, and that way, if we do not get to all the questions, we can certainly follow up with you after the webinar. So I'll wait to get some questions. Give it another minute. Okay, Jeff, if you were to say, what would be the advantage of the monodisperse UHPLC particle as it compares to both fully porous or the industry standard core shell technology as it stands now? What would you say is the advantages over both technologies?
Well, comparing it to fully porous material, you're going to have higher efficiency, and I showed that earlier, but we've seen that across the board. You have similar surface areas, but the efficiency piece, anywhere from 40 to 60% efficiency. It's giving efficiency similar to core shell technology. Comparative to core shell technology, you have more retention, which is exciting, and you have the ability in general to scale to larger prep columns in 21.2 or 30 or 50 millimeter IDs. You also have the surface area piece, so more interaction with your bonded phase, which will drive the retention and then also impact your selectivity. So I think those are the critical factors comparative to the two technologies. And so that's really what we're excited about from the innovation perspective.
Okay, thank you. And I have another one here. It says, is the half back pressure compared to fully porous particles or core shell?
So the fully porous particles, so the back pressure in general across all of these different particle technologies is due to the particle size. So this material in a 1.7 is going to give similar back pressure to a fully porous 1.7, or for that matter, a superficially porous 2 micron. You're going to get similar back pressures. But what I would say is, if you're getting efficiency on a monodisperse 3 micron comparative to a fully porous 1.7, that gives you something really exciting. That is originally why we really were excited about the core shell technology. But now you're getting fully porous retention with that secondary benefit. So that's pretty exciting there. Yeah, so again, that 3 micron monodisperse particle is going to give you a lot of what the superficially porous gave you, but all this extra stuff too.
Okay, unfortunately, that is all the time we have today. If you had a question that we did not get to, we will follow up with you via email. I also want to remind everyone that we will be sending out a link to watch the recording of this webinar and a link to view the slides should you need to do so. Thanks again, Jeff, for a terrific webinar. If you are interested in learning more about this new technology, we have one more webinar in this series. Part 3, as Jeff mentioned, will discuss monodispersity and its applied use in oligonucleotide separations without ion pairing additives. It will be held on May 14th at 1 p.m. Eastern Time. You should receive an email soon with a link to register. Thank you for attending, and we hope to see you on May 14th for the final part of the series. Hope everyone has a great rest of the day, and we'll end the broadcast now.